Last time we introduced hyperbolic functions. We also introduced inverse of hyperbolic functions. We said that hyperbolic sine and hyperbolic tangent are both one-to-one functions, so they have inverse, which is denoted by inverse hyperbolic sine and inverse hyperbolic tangent. For hyperbolic cosine, it is not one-to-one on its domain, so as you saw, we just limit the domain to positive part of x-axis. So it becomes one-to-one function. When we write down y equals to inverse hyperbolic sine of x, it means that hyperbolic sine of y is equal to x. When you define inverse hyperbolic cosine of x to be y, the meaning of that is the hyperbolic cosine of y is equal to x. And we saw that when we write y equals to inverse hyperbolic tangent of x, the meaning of that is hyperbolic tangent of y is equal to x. When you're taking the derivative of inverse hyperbolic cosine of x, it is equal to 1 divided by square root of x squared minus 1. The derivative of inverse hyperbolic sine of x is equal to 1 divided by square root of x squared plus 1. We can find the derivative of the rest of the inverse hyperbolic functions. For example, the derivative of inverse hyperbolic tangent of x is 1 divided by 1 minus x squared. The derivative of inverse hyperbolic cotangent of x is 1 divided by 1 minus x squared. The derivative of inverse hyperbolic secant of x is negative 1 over x times square root of 1 minus x squared. And finally, the derivative of inverse hyperbolic cosecant of x is negative 1 divided by absolute value of x times square root of 1 plus x squared. So now you can use the fundamental theorem of calculus. The fundamental theorem of calculus say, hey, as long as you have the antiderivative, you can define the integral. So the integral of du divided by square root of a squared plus u squared is nothing but inverse hyperbolic sine of u divided by a. Don't forget the constant of integration. If you have the integral of du divided by square root of u squared minus a squared, this pattern is inverse hyperbolic cosine of u divided by a. If you have a pattern in your integral, du divided by a squared minus u squared, depending on the behavior of u and a, as long as u squared is less than a squared, this integral is 1 over a inverse hyperbolic tangent of u divided by a, and as long as u squared is more than a squared, it is 1 over a inverse hyperbolic cotangent of u divided by a. The pattern of the integral of du divided by u times square root of a squared minus u squared is negative 1 over a inverse hyperbolic secant of u divided by a. And finally, as long as you see the integral of du divided by u times square root of a squared plus u squared, this guy is equal to negative 1 over a inverse hyperbolic cosecant of absolute value of u divided by a. So again, these help us to calculate the integrals a little bit easier. So whenever you see the integral of the type on the left-hand side, you can easily calculate that integral using inverse hyperbolic functions. So we just learned that the integral of du divided by square root of a squared plus u squared is nothing but inverse hyperbolic sine of u divided by a. So in this example, I ask you to evaluate the following integral. The integral of dx divided by square root of x squared plus 16, and x is bounded between 0 and 3. Well, this integral dx divided by x squared plus 16 is nothing but inverse hyperbolic sine of x divided by 4. Why is that? If you rewrite this guy as the integral of dx divided by square root of x squared plus 4 squared, we can easily recognize the pattern. You can switch this around as well. You can write it as 4 squared plus x squared. It doesn't change the fact that it is indeed inverse hyperbolic sine of u divided by a. In this case, your u is equal to x and your a is equal to 4. So this integral is inverse hyperbolic sine of x divided by 4. Now plug in 3, then plug in 0 to be able to simplify this integral. So you have inverse hyperbolic sine of 3 divided by 4 minus inverse hyperbolic sine of 0. Remember the behavior of inverse hyperbolic sine. At 0, it is going to be 0. So you end up with inverse hyperbolic sine of 3/4. You can use a calculator to approximate this number, or you can go back to the formula that we introduced last time and write it in terms of ln. Remember that last time we proved that inverse hyperbolic sine of x can be written as ln of x plus square root of x squared plus 1. So let's plug those in. Inverse hyperbolic sine of 3/4 can be written as ln of 3/4 plus square root of 3/4 to the second power plus 1. Well, this guy is nothing but ln of 2. You could simplify this as well to see all the algebra behind it. This is ln of 3/4 plus square root of 9/16 plus 1, which in turn equal to ln of 3/4 plus, if you take common denominator, you get 16 plus 9, which is 25. So you get ln of 3/4 plus 5/4, or you get ln of 8 divided by 4, or ln of 2, as you see on the right-hand side. So that's the use of hyperbolic functions. When you see the pattern like this, the integral of dx divided by square root of x squared plus 16, this is nothing but inverse hyperbolic sine.